In this video, we're going to explore the chain rule for nested functions and their derivatives. The kind of relationship we're looking for in this scenario is something where the functions are nested. For example, x squared is inside the exponential, or ln of x here is inside the sine function. So it's not a product, it's not a quotient, this is a nesting idea. The way the rule works is we take the outside function, so here the e or the sine, and we take the derivative of the outside function, but we keep the inside the same. When we do that, that doesn't seem like we're doing much different. We'd just be taking the derivative of the exponential. But to account for the fact that what's inside isn't just an x, it's actually a more complicated function like x squared or ln of x, then we have a multiplier at the end where we multiply by the derivative of the inside function. This is the form that we usually would paraphrase or express in English. We'd say the derivative of the outside with the inside the same times the derivative of the inside. The Leibniz notation, which is this d form that we use for derivatives as well, it has this nice structure to it, which makes it look like what we would expect with fractions and cancellations. If we're talking about the derivative of f with respect to x, and f's what's outside here, you can phrase it as the derivative of f with respect to the inside g, and then multiplied by the derivative of the inside g with respect to x, and it feels like these g's cancel in some sense, and we get back to the derivative we're actually interested in. This doesn't tend to be as helpful during calculations, but it can be a nice mnemonic for the relationship between functions of x that map into a new function g, and then g is the input for function f, and we will return to this theme throughout the course. For now, though, we're going to focus on this form because it makes calculation a little more intuitive. Let's take that e to the x squared example we just saw, and we'll put labels on it for this first time through. The idea is I have e to the something. If I were to write that as a function of x, I would have written it as e to the x. What we're looking at here is what happens when we replace that x with an x squared. And that's what we're calling our g of x. So, what does the formula for the derivative tell us? It says take the derivative of your original function. The derivative of e to the x is e to the x again. Except our x isn't just an x anymore, it's an x squared. We would paraphrase that as the derivative of e to the x is e to the x. That's fine. When we're using the chain rule and have nested functions, though, we would say it slightly differently. The derivative of e to the anything, that's our function of x, whatever we have in there, is going to be e to the same thing times the chain rule effect. So how does that play out here? The derivative of e to the x is e to the x. The derivative of e to the x squared is e to the x squared. That's what we have here, but then the chain rule says we have to account for that x squared being in there, not just an x. And so we multiply by the derivative of that x squared, which is 2x. If this is new to you, it does get easier with practice. Keep an eye mainly on the inside and outside relationships of these functions. The x squared is inside, so we deal with it later. The outside function is e to the something. E to the x is our base. We take its derivative first, then multiply by the derivative of the inside. Here again we have x to the 4 inside another function, ln of x in this case here. Let's do that same mnemonic. The derivative of ln of x is 1 over x. So the derivative of ln of anything is going to be 1 over the same thing times the derivative of the inside. That's the chain rule part. So all of the basic rules we learned about derivatives of simple functions apply here. We're just extending them with this chain rule. So the derivative of ln anything, x to the 4, is 1 over the same thing, so 1 over. x to the 4. Then we multiply by the derivative of the inside. That's just the x to the 4. It doesn't matter where it ended up here. This is our inside. And so we have 4x cubed as our derivative of the inside. That would be a perfectly valid derivative. Of course, we can tidy it up because we have powers of x in both the top and the bottom. We could simplify that to 4 over x. Here we have an expression that looks like it could be a quotient rule, but because there's no x's in the numerator, we can use the quotient rule, or we can simply write it as the derivative of a single function, 1 plus x cubed, all of that to the negative 1. And then it becomes a nesting function where we have the inside and the outside function. That tends to be easier. The quotient rule is overkill when there isn't a function in here. You can use it, it's totally fine. Just be aware that your function is on the top is 1, and so the derivative of the top, which is needed at some point, is 0. So if you're going that way, that's fine, just be careful. This tends to be simpler, and most students make fewer mistakes using this approach. Here we have a power, that's our outside function, and the rule for powers is bring the power down front and subtract 1 from the power. And then what we do is we keep the inside function identical. So we have our 1 plus x cubed again. Now this was not just a simple x, so we have to follow up with the chain rule, which says take the derivative of the inside. So we take the derivative of the inside, 0 plus 3x squared. And this is worth tidying it up a little bit, just so we can see what the pieces are. We have an exponent -2, so that can be moved to the denominator for presentation. We have -3x squared on the top left over, and that would be the result of this derivative. If we graph this function here and asked what's the slope at any point on that graph, this much more complicated formula would give us an expression for the slopes of the original graph. Practicing one more time here. Here we have a sum, so don't get distracted by all the new rules we've learned. If we have a sum, we can simply take the derivative of the first term all by itself, and we know how to take the derivative of a power of x. It's 4x cubed in this case. In the next expression, we have an inside function, which is the 3 to the x. So we take the derivative of 10 to the something, very much like an e, is going to be 10 to the same thing again, ln of 10. And that feels a little different, but just remember that the two expressions here together all reflect the derivative of x of 10 to the x is equal to 10 to the x ln 10. That's all one thing together. The fact that there's a 3x gets captured in the next term. This part here is the chain rule, or comes from the chain rule, the derivative of the inside, which is the derivative of the 3x itself. So we have a sum. We don't have to use any complicated relationship rules for that. We just take the derivative of the first plus the derivative of the second, and then we dive in a nested way to the derivative of the second. The 10 functions on the outside. The derivative of 10 to the something is 10 to the same thing, ln 10. And then, oh yeah, it was a 3x inside, so we take the derivative of the 3, and there's no more x's left, so we stop our derivatives there. There's no more inside functions at that point, so we're done. As a last example for this video, we have the question of taking the derivative of e to the root x. If you'd like, take a try at this first, and see if you can identify the solution. We'll go through the steps in a moment. The most helpful thing whenever we have roots is to rewrite that as a power. Because we have rules for powers, we don't typically remember the rules for roots in quite the same way. If we take the derivative of e to the x to the 1/2, remembering that this is the inside part here, then we can use our rules from before. The derivative of e to the anything is e to the same thing again, times the derivative of the inside, and the rule for the inside derivative is bring the power down front and subtract 1 from the power. Looking at the forms we have here, it makes an easier match if we start writing these as roots again. and noticing that this is a negative power, so we actually have 1 over the square root of x. And if we scan down, we see that c would be the correct answer for this derivative.